Hello, my name is William McKillop. Today I'm going to be telling you about Lab 1 and the findings I had. So the purpose of this lab is to determine the billiard ball position over a given time interval, given that the object is moving at a constant velocity. So with glow script, we can apply Newton's second law to design a model from the collected data. Then we compare that data from our observation to that of the computational model to determine the difference in the object's position and time and a little bit of foreshadowing into the future. The results show that the external forces such as gravity and friction had little effect on the motion, which is similar to the computational results where there are no external surroundings within the calculation. So, relevant laws and formulas obviously is acceleration and the velocity update formula. And as we know, Newton's first law of motion is if an object is at rest or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line. And Newton's second law is basically F equals ma. It describes the changes that a force can produce on the motion of an object. And the force equals zero indicates an object is moving at constant velocity unless it is acted upon by an external force. So for the lab procedure, I used the billiard ball as the object of motion, and I found a flat wind table as the surface. And I recorded the ball moving constantly along this surface. I uploaded the video to Tracker and, applied the appropriate scaling and measurements to eventually produce a graph. And I altered the glow script starter code to fit the conditions associated with the experiment. And so here are the specific measurements for the ball I used. And I calculated the initial velocity so I can start, plugging into the formulas. I decided that the final time was going to be at exactly 1 second. And just for reference, the 15 frames per second is where that's at. And then I traveled 0.77 meters in that time. So first, the video was calibrated as I was just explaining. The ball traveled 0.77 meters, and the diameter of the ball was 0.053 meters. Um, I trimmed the beginning and the end of the video in order to just focus on what we exactly wanted from the video. Motion was accounted for in the X and Y direction, but not for the Z direction. It's one thing to note. Although this is a constant velocity experiment, forces such as friction and gravity in this experiment affect the velocity. Therefore, it cannot be stated that the object traveled at a constant velocity, unfortunately. So this is kind of what my code looked like. Um, I just altered the few things. I obviously copied the starter code and just plugged in my specific values into this code. And eventually I got these graphs from GlowScript. Yeah. This computational model is what will be used to display the expected motion of the object. This will be compared to the observational model results on Tracker. And it's the same thing with the observational results from Tracker. It will be compared to the one on GlowScript. If you want to look at that, that's kind of what I got from that. Computational versus observational results. The computational results are shown using the solid blue line, and this line illustrates the motion of the ball without any outside forces. The red dots represent the observational results where friction and other surrounding forces affect the object. As we can see toward the end of the time, the red dots kind of get away from the blue line, and that just shows, uh, eff- the effect of friction and other forces on the object. But at the beginning, it was relatively the same. What if you were to flip the axis for the graph, the object's motion would travel in the negative x direction? Because velocity includes both direction and magnitude, the flip of the axis would cause the motion to change directions. However, speed would not be affected as it is a scalar. In this situation, the ball would now travel to the left instead of the right. So we can draw this conclusion. We know surroundings that apply a force on the object can affect its motion, as we saw in the observational results. This was observed while comparing the beginning of the observational results to the computational results. The lines were overlapping each other. This indicates that they are on the same path and therefore support Newton's first and second law. The computational model indicated no net force in the object in motion. Therefore, The object continued to remain in motion. This proves Newton's first and second law as true again.